So I'm going to talk to you guys today about a topic that is all over the news, on the lips of every reporter, a lot of startups, the Prime Minister. I want to talk to you guys about AI and machine learning. So first thing as first, I want to take a quick poll. How many of you have heard of AI and machine learning in the news, outside of war games? Of course. OK. Keep your hands up, though. Keep them up. How many of you feel like you have a pretty decent understanding about what that actually means? OK. Of you guys who still have your hands up, how many of you think you could have like a reasonably good cocktail party conversation with a computer scientist about this topic? OK, there's like 4 of you left. So this is my goal, is for the rest of you to join these 4, and that if you are ever at a cocktail party and run into a computer scientist, you can have a pretty decent high-level conversation about machine learning and artificial intelligence. Don't worry, that's never actually going to happen, because computer scientists don't go to cocktail parties. But if it did, you'd be ready. OK, so this is my agenda. I want to start off with some definitions, some terminology, because I think that's super important in this space. Then we'll get into an example of how does it actually work. And I'm going to use a machine vision problem for this, so identifying pictures. It's going to be very high level. Everything that I'm going to show you is a gross oversimplification, but it will work for today's purposes. And then we'll take a look at how can you actually use it, and how could it work for you in your business? Or roughly work for you guys? OK, so first off, some definitions. The term artificial intelligence is one that gets thrown around a lot in the industry by the press, by companies like Google. You actually won't hear us use the term artificial intelligence very much, if at all, for 2 reasons. Number one is it's actually a really broad term. The technical definition of artificial intelligence is machines that perform thinking-like actions. So technically, your calculator is artificially intelligent, and so are your ABS brakes. But nobody would consider those things to be AI. And that's actually the second reason why you don't see us use it very often, is as soon as something becomes commonly accepted in society, nobody thinks it's AI anymore. If we rewound the clock back to the advent of the original mechanical adding machine, the very first calculator, people were up in arms that it was going to put accountants and bookkeepers out of business. That clearly did not happen. So you won't see us talk about AI very much. But it is technically correct, just very broad. Within AI, there is a subset of techniques called machine learning. You will hear us talk about this a lot more often. Machine learning is a really interesting topic. As a subset of AI techniques, it is basically computer programs that get better with use. Within machine learning, there's a subset of techniques called deep learning. And this is what all the fuss is about. If you see headlines about AI or machine learning these days in the press, or a startup coming out saying, oh, our system is AI-powered or machine learning-powered, this is almost certainly what they're talking about. Deep learning is a set of techniques. It's fundamentally just a different way to program a computer. And it's based on a neurological model, a biological model of how a biological brain works, like your brain or my brain, or more accurately, like an ant's brain or a fruit fly's brain, because we're not that sophisticated on it yet. And actually, that's probably even reaching a little. But a great example of a program that is based on this kind of technology would be Google Translate. Today, the modern version of Google Translate is almost completely underpinned by deep learning. And if that sounds like still like a really high-level explanation, don't worry, we're going to get into our next section. So that's our terminology. AI is this really broad term. Machine learning are programs that get better with use. And deep learning are these totally weird, different set of programs. They're a totally different way to program a computer inspired by biology. OK, how does that actually work? So I am going to run, as I mentioned, run you guys through a machine vision example to illustrate this. I'm going to leave a lot of stuff out. I'm going to grossly oversimplify things. That's totally OK. The godfather of machine learning, Dr. Geoffrey Hinton, works like on the same floor as me, just around the corner. And he roughly describes it this way. So if it works for Jeff, I think it'll work for us today. So if I went and asked you to write a program for me on how to identify whether a picture was of a hot dog or not a hot dog, for those Silicon Valley fans out there, almost every programmer in the world would approach it through something called deterministic programming or feature engineering. Pretty much every computer program you have ever used was programmed this way. From Microsoft Excel to Super Mario Bros. 1 to the entertainment system in your car were all programmed with feature engineering. Basically what would happen is you would sit down at your favorite dev environment and you would start writing your program called, let's say, isHotDog. And you would have to define all the things that make a hot dog, like, does it have a bun? And is the meat tubular? And is it sort of reddish brown? And are the ingredients questionable? And does it smell kind of oddly appealing? And this has a couple of problems. Oh, jumped ahead. This has a couple of problems. Number one is that it takes forever. Okay, so it's not unheard of for a simple machine vision program, like our hot dog, not hot dog program, to take about 500,000 lines of code. Right? That's a lot of time sitting at a computer drinking Red Bull and eating Hot Pockets to write that code. So that's one problem. The other problem is that because it's so big, it's expensive, computationally expensive to run on a computer. So you need a lot of computer horsepower to do it. And the last thing is that it's brittle. And what I mean by brittle is that if the person programming it was sort of inelegant in the way they defined one of the things that make a hot dog, or if they left one of them out, it's really easy for the program to get confused. And so something that kind of looks vaguely hot dog-ish would get identified as being a hot dog. And a totally relevant, actually legit hot dog, if it looks slightly outside the norm, would get identified as not a hot dog. And as a result, for the longest time, computers were really bad at problems like this, because feature engineering, deterministic programming, is just not good at solving problems like this. The real world, it turns out, is just too messy for you to sit there and write in all of the rules on how to make it work. Fortunately, there's a totally different way to program a computer, and that's the idea of a deep neural net. So anyone here have a degree in biology, neuroscience? Take high school biology. Know what a brain is? Okay, good. We're like halfway there. All right, so this is inspired by biology, inspired by the way that our brains work. And much like your brain is a big structure, a collection of neurons, these little gray cells that connect to each other, and it's their structure that does the programming in your head, or the computations in your head, a simulated neural net is the same. So it's made up of a bunch of neurons, and each neuron has a few simple parts. The first thing is a node. All you need to know about a node is that it's a really simple mathematical program that adds vectors together. Do you guys remember vectors from high school algebra? If you don't, they're big tables of numbers. Actually, they don't have to be big. They're just tables of numbers. That's all you need to know. So all a node does is it takes tables of numbers and adds them together. Okay? Then attached to that node is an edge. There's actually usually many edges. We'll just look at one here. An edge is simply a pathway to take the result of that node. So it took up a couple of tables of numbers together, added them together, and then we're transmitting that new table of numbers along this edge to a new node, or other nodes. On that edge, there's something called a weight. And a weight is a percentage value that, for our purposes today, goes from 0 to 100%. Okay? If I tune it to 0, and it multiplies against the table of numbers that's transmitting along that edge. Okay? This is the only math you're going to need to do right now. Okay? If I tune it to 0, anything times 0 is 0. Excellent. Okay. If I tune it all the way up to 100, anything times 100% is itself. Okay, so this has the effect of either shutting that edge down. If I turn it to 0, it basically says, look, node, I don't care what you added together. I'm going to multiply it by 0, which effectively negates whatever you did. I'm just going to turn it into 0. If I tune it to 100%, it says, OK, I'm going to multiply whatever you did by 1. I'm just going to let it pass through unimpeded. And I can go anywhere between those two values. It has the effect of like tuning, sort of choking off that edge or letting the information pass unimpeded. So we're going to have big structures of these neurons. All they're going to do is take tables of numbers, add them together, transmit them along an edge to a new node, and on the way they're going to get multiplied by this weight, which is going to be somewhere between 0 and 100%. Okay, that's the sort of most complicated part that we need to talk about. So we array these nodes into big structures. So this still might seem a little bit hand-wavy, and like, how does that actually identify hot dogs? Don't worry, I'm going to show you. So we start off with a picture of a hot dog. You guys agree this is a hot dog? Hot dog, yes, no, hot dog. Okay, cool. So we turn that picture of a hot dog. First thing we do is actually carve it up into pieces. So you see I've done that here. We carve it up into little slices. Each one of those little slices is going to be represented by a table of numbers. Fortunately, this is really easy for computers to do because like a JPEG on your phone or in your computer is already just a big table of numbers. The computer actually assembles it into a picture for you. So we're going to take the table of numbers that represents each one of these little squares, and we're going to feed it into a first layer of these simulated neurons called input neurons. And they already have some data in them, which comes to represent lines. And what we're basically doing with this first layer is looking for lines. We take each one of these little slices of the picture of the hot dog, we feed it into the input neurons, and those input neurons effectively say, do I see the line that I've been pre-programmed with? Do I see a line that goes like this, or that swoops down, or that curves to the side, or a diagonal line, or an up-down, or a down line, whichever one, okay? They then take their answers, which are just big tables of numbers, and pass them along edges to new nodes in the next layer. Okay, and those nodes have the effect of looking for combinations of lines. They take their answers, pass them along their edges to the next layer of nodes that are looking for combinations of lines. By the time you get to combinations of lines, that could be something fairly complex, like a bun or a pickle or ketchup or something that would identify this thing as being a hot dog. Incidentally, these layers of neurons, this is why it's called deep learning. It's not like some metaphysical, like, whoa, that's deep, man. It's about the number of layers deep that the network is. And turns out, this is when I said that this was inspired by biology, you can do a lot with a few layers. So much so that you, and me, and all the rest of us are only 6 layers deep. What I mean by that is your prefrontal cortex, where like your conscious mind exists and like most of your, what you think of as you happens, is a neural net that's 6 layers deep. So the more layers you have, the more complicated stuff you can do. By the time you get to 6, you can do everything that you could do. All right, so in our example, we have lines, then next layer looks for combinations of lines, next layer looks for combinations of those lines, and then eventually we get to a layer that says hot dog or no hot dog. So when we start with a net where all those, remember those weights on the edges, that percentage value from 0 to 100%? We start with them just being random. We just randomly assign them. And as a result, when we feed in our picture, we get a random answer. It says 26% likely that this is a hot dog. But we all agreed right at the beginning, 100%, and there were a couple of people who didn't put up their hands, but 100% we were pretty sure that this was a hot dog. It's because we haven't actually programmed this net yet. So the typical way to program a computer is I sit down, I start writing in all the rules. Here I start with a net with randomly assigned values. Then I take a picture, or an input, in this case a picture of a hot dog, where I know the answer. And I feed it into the net, and I get a bad, wrong answer at the other end. Then I have to do something called training. To do this, I basically write a little computer program that goes through, and it goes to each one of the weights on every one of those edges, and it tweaks them up a little bit towards 100%, and it says, hey, does this number, this 26% number, get closer towards 100%? Because Adam told me when he fed me this picture that 100% this was a hot dog. So am I getting closer towards the right answer? If not, okay, what if I tuned that weight down closer towards 0? Does that make my answer better? If not, okay, I'll just leave this edge alone and I'll go on to the next one. And it does this for every single edge, for every weight in the network. And as a result, the structure of the net changes. Some edges get a little bit better connected. Some edges get a little bit worse connected. They get tuned closer to 0. Their effect gets muted out. And we get a progressively better answer. But even if we got all the way to 100%, we've only trained this on one picture of a hot dog. So if all of a sudden I got a different picture, like that one that I showed you before where it was like on a pita and it totally fooled the old kind of system, this one might get fooled too. Turns out we can't just train on one picture. We need lots. So we get thousands of pictures of hot dogs, and we do the exact same thing for each of them. We carve them into slices. We take each slice, we feed it into the net. The first layer looks for lines. The second layer looks for combos of lines. The third layer looks for combos of combos, et cetera, until it says hot dog, not a hot dog. And then because we know that all of these pictures for sure are pictures of hot dogs, we do the same thing. We go back in and we tweak the weights up and down. We don't manually do it. It'd take us forever. We write a computer program that does it, tweaks them up and down, tries to get that number closer towards 100. After we fed thousands of pictures of hot dogs in, we end up with a net that's changed a lot. A lot of the edges have been turned off. Their weights have been tuned completely down to 0, so the two nodes are no longer connected at all, functionally. Some of them have been tuned all the way up to 100%, varying degrees. So our net changes a lot. And we end up with a program that is really great at identifying pictures of hot dogs or whether they are not hot dogs, without anyone having ever had to sit down and say, a hot dog is a lunch food made of tubular ground raccoon in a yellow strange bun with ketchup and mustard, unless, of course, you're in Chicago, in which case that's outlawed, et cetera, et cetera. Nobody ever had to do that. All we had to do was get thousands of pictures of hot dogs, feed them into this thing, and then let a computer program twiddle the weights up and down until all of a sudden the structure of the net changed such that it's able to identify pictures of hot dogs. So what does that actually look like? Here's an example from a facial recognition net. So on the left, these are the kinds of things that the first layer in the node, that those input neurons are looking for. So you'll see that these are those are individual pixels. The hot dog, the picture that I had carved up, those slices were way too big. You carve it up into really, really tiny slices, but the visual didn't work as well. So then the second image here, that's layer 2. That's looking for combinations of those input lines. By the third layer, that's combinations of combinations, you can start to see recognizable features, eyes and noses and ears and mouths, et cetera. By the fourth layer, we can see definitely this is a net that's trained to look for faces. So as a concept, this has been around for a long time, since actually Alan Turing's time. So this theory has been around since then, that this was a good computational way to solve problems. But it remained a blackboard theorem until very recently, because while you could mathematically prove that this was a great way to do things, nobody had a computer powerful enough to do all of it. Because even though it's very simple, we're just taking vectors and multiplying them by percentage values and then passing them through this net, there's nothing mathematically complicated about it. We need a lot of these nodes. That hot dog net that I showed you was really, really, really simplified. So this is a multi-layer perceptron. It's the same kind of net that I drew for you guys. It is identifying handwritten digits. It's 4 layers deep, and it's only displaying 2% of its synapses. Synapses are those edge connections. Because if we displayed all of them, it would just be a big white dot. Because there's so many of them, millions of these connections. So it turns out we just didn't have computers powerful enough to do this until very recently. In fact, really just in the last 5 years did we have access to cloud computing from providers like us that would allow you to train these nets. Turns out it's the training, it's the twiddling the weights up and down that takes all the computational horsepower. So it wasn't until about 5 years ago that we could even do this. The theory had been around since the 40s, but it remained theory until now. The other reason is we just didn't have enough data until very recently. And for the most part, we have you guys to thank for that, and us and other web companies, because the web is the best source of highly structured training data for these networks. So is that roughly almost even a little bit clear to you guys, this idea that every program you've ever used up until now was feature engineered, someone sitting there writing in rules, but a deep neural net is programmed in an entirely different way? We start with this network of nodes that just really add vectors together and multiply them by weights, and then we feed it lots of information where we know the answer, and it trains itself, and then eventually we have a thing that can identify pictures of hot dogs or stop signs or whether a transaction is fraudulent or all kinds of different things. Is that roughly clear? Okay, there's 3 people nodding their heads and then a bunch of people sipping water and being I don't want to be the guy who says that I don't know. Okay, cool. So what can it do? One of the first things that we threw this kind of computational architecture at Google was translation. It turns out it was really, really good at translation. And there's a bunch of reasons for that. It turns out language is really messy, the English language especially. Do you guys remember Google Translate 5 years ago? And it sucked. The Translate team isn't here, so I can say that. It sucked a lot, right? You ever play the game where you take a sentence and you put it into Translate and you put it in another language and you're that's not right. And then you translate it back to English, you're whoa. That's not even close. If you try to do that now, it doesn't really work. You put it in the other language, it looks okay. You put it back into your own language, and it's fine. It's almost the same thing, if not exactly the same thing that you put in the first place. And the reason is that 5 years ago, Translate was deterministically programmed. It was feature engineered. It was basically taking two dictionaries and looking up the words. It wasn't using individual words, it would use phrases, but I was still deterministically programmed. Whereas now, it is a net that underpins it. And so it turns out when you take a word and you turn it into a vector, it brings with it a lot of really cool information. So you train a network on how to vectorize words based on a huge corpus of information, like let's say all of the English, publicly available English language books. All of a sudden the Google Book Project starts to make a little more sense, where we take like books that were no longer under copyright and scan them in using optical character recognition. We can train a net on what the words actually mean. So I have a quick demo for you on this. If you take the vector for the word Rome, okay, you take the word Rome, you vectorize it, which becomes a big table of numbers, and you subtract the vector for the word Italy. Okay, it's just another big table of numbers that represents the word Italy. And you add the vector for the word France. What you end up with is a vector that's fairly close to the vector for the word Paris, even though nobody ever told it that Rome is a city as to Italy, as Paris is a city as to France. They're both countries in Europe. Countries have capitals, etc. Nobody had to program that. The system learns it by digesting huge amounts of language. I mentioned that the training is the computationally hard part. That's where you need access to a data center or a cloud computing instance in order to be able to do it. But once the system is trained, it's actually a fairly efficient way to do complicated tasks. So anyone have Google Translate on their phone? Okay, next piece of homework while you're watching War Games tonight, download Translate and give this a go. So this is the latest version of Translate, and it features a, oh man, thank you. I'm very sick because it's back to school and kids are where germs come from. So this will run on your phone, okay, in airplane mode. It's not doing the computations in the cloud, it's doing it on your phone. So what we see here is someone holding up their phone to a stop sign, or an exit sign rather. It is reading the text, translating it into another language, rendering that text back in the same original font, wiping out the original English word and inserting the new word in Arabic or German or Spanish or whatever, all in real time, and all of the computation is done on your phone. If you went to the best computer scientists in the world 10 years ago and said, this is what I want to do, I mocked this up in Photoshop and I want you guys to make this, they would tell you that it was impossible. There was no way you could do it, and if you did, you would have to have the phone plugged into a giant server bank to be able to do it, because they probably would have been thinking about it in feature engineering terms, in deterministic programming terms. But a neural net can do this much faster. It's still a pretty big program. You can download about 5 different languages. Right now on my phone I have 3. All the computation happens on your phone. It'll work in airplane mode. It'll work in a submarine if for some reason you needed to translate stuff on submarines. So very efficient once it's done. It's being used all over industry. You've probably seen a lot of these news stories. This is one from the health world, where we partnered with the Department of Ophthalmology to identify something called diabetic retinopathy. Anybody in the room know someone with diabetes? Okay, odds are all of us should probably be putting up our hands. So one of the horrible side effects of diabetes is something called diabetic retinopathy or diabetes blindness. Basically what happens is your retina, the blood vessels degrade and they start to leak. Not everybody who has diabetes is susceptible to this, but some people are. So one of the things that happens if you get diagnosed with diabetes, your doctor says, oh man, I need you to go to an ophthalmologist to make sure that this isn't one of the things that might happen to you if you let your blood sugar, insulin levels get all out of whack. And so an ophthalmologist spends a lot of time seeing people. They come in through their really boring waiting rooms with no posters, and then they sit down and they look into their eyes, and 9 out of 10 of them they go, no, you're fine, you're fine, you're fine. You might have a problem. Why don't we come and talk about, is it surgery, is it drugs, what's our treatment plan, etc. We trained a net on how to recognize the early stage signs of diabetic retinopathy. We trained it on 12,000 instances that the Harvard Department of Ophthalmology had diagnosed. We can now diagnose diagnose diabetic retinopathy at a higher rate of accuracy than the Harvard Department of Ophthalmology can. Which initially sounds terrifying if you're an ophthalmologist. You're like, I just invested in all these new posters. I'm going to be out of business. Fortunately, though, this is actually the best news ever for you, because you used to spend a huge amount of time doing effectively nothing, right? Looking into healthy people's eyes and telling them to go home. Now, the GP can scan their eyes using an ophthalmoscope, which is that thing that they use to look into your eyes. That's another thing you've learned today, an ophthalmoscope. And the only people who get sent to the ophthalmologist are people who are at risk of diabetic retinopathy. So this is a huge boon for them in terms of productivity. But you guys are all marketers. What the hell could this mean for marketers? So this is a campaign that ran in January in Moscow. Anyone familiar with this campaign? It was in Ad Age, like the day that it launched. And they were going after a really specific audience segment, which is existing luxury car owners, and in particular, existing luxury SUV owners. So they had a digital signboard, which is that thing that's circled in red up there. And they hooked a camera up to it, and the camera pointed down the highway, looking at all the traffic that was coming towards it. They took the feed from that camera, and they fed it into a image recognition API. One of the really cool things about image recognition APIs, an API is an application programming interface, incidentally, for those of you who don't know. It's basically a computer program for hire, like a little mercenary program. So they fed their data stream into this mercenary program, and they said, I'm looking for luxury SUVs. And the system just spotted luxury SUVs for them. And they were able to update the billboard to say, did you know you get 15% more horsepower, 20% more trunk room, all for 600 rubles less a month? Maybe it's time to switch. And in one fell swoop, with a camera and like $1,000 worth of API calls, they were able to take the least targeted medium since skywriting, really, and turn it into the most targeted medium, having a one-to-one conversation with people driving down the highway. So I think one really important thing to remember is no matter what, this stuff is a tool. It's not the carpenter. We're not going to be working for the machines in 5 years. It's only as good as we, the carpenters, make it. Having great tools does not mean we will have great answers. It's still going to be in our hands. So how can you use it? Good news is, you probably already are. It's baked into the background of pretty much all of our products at Google. Anything to do with our automated targeting, automated bidding is all underpinned by machine learning at this point, and deep learning. We have some elements to do with creative editing that are increasingly coming to the fore, and optimization and attribution, of course, are also underpinned by this. A great example is our universal app campaign, is almost completely underpinned by a set of neural nets to do everything from creating display ads for you to then approve and put out in market, to targeting and bidding. If that isn't enough for you, I mentioned APIs from the Moscow example. We have a bunch of them, more coming all the time. So we have ones for vision, for video, for the perspective one is to do with the sentiment analysis of text, speech to text and text to speech, and a whole bunch of others. You can use these. You don't need to be an expert in machine learning. You don't even need to be an expert coder. Anybody who knows basic Java or HTML can call these things and make use of them. If that's not enough, all of the system, the base architecture that we base our systems on at Google, we open source through something called TensorFlow. It's the most downloaded machine learning library on GitHub. It's a whole bunch of pre-trained nets, pre-built architectures that you could use to build something. If you don't see that you could build it using our APIs as a plug and play, you could go and build it yourself. For that, you do need to know Python. You do need some machine learning expertise, but you don't have to start from scratch. If you want to do this within your business, the best place to look is places where you're making lots and lots of decisions, right? Because you want to be able to automate it. You're just like, oh, we have too many of these decisions to make in an hour. Places where you have lots of old data, old pictures of hot dogs to train the thing on, lots of new data, new streams of data to feed into the system, and where there's some meaningful business outcome for you, because it's not cheap, right? So what did we learn today? It's a new way of programming computers, totally different than the old. They're trained instead of programmed, so we train it on lots of existing data instead of sitting there and manually writing in rules. It's embedded in pretty much all of Google's products at this point. You want to find places where you're making lots of decisions, you have lots of data, and there's a real impact on your business. It's a hammer, not a carpenter. And that's it. Thank you.